Good morning, students. Today, our topic is radiation from accelerated charges. Radiation from accelerated charges. A stationary charge produces electrostatic field only. A stationary charge produces electrostatic field only. A uniformly moving charge produces electromagnetic field of short range. So, they cannot radiate the electromagnetic energy. The electromagnetic energy can be radiated only if a charge particle is accelerated. The electromagnetic energy can be radiated only if a charge particle is accelerated. When a charge particle is accelerated, then electromagnetic energy will be radiated. Now, retarded potential, and we know that in the previous classes that E is equals to minus del phi minus del A by del T, B is equals to del cross A, and we know the Lorentz condition that del dot A is equals to mu naught epsilon naught del phi by del T, and mu naught epsilon naught is equals to 1 upon c square. So we can write del dot A is equals to 1 by c square del phi by del T in homogeneous equations. Del 2 phi minus 1 by c square del 2 phi by del T2 is equals to minus rho upon epsilon naught, and del 2A minus 1 by c square del 2A by del T2 is equals to minus mu naught J. These are the inhomogeneous equations in terms of A and phi. Now here J is current density. In the static case, equations 3 and 4 becomes, in the static case, del 2 phi is equals to minus rho upon epsilon naught, and del 2A is equals to minus mu naught J. Solution of above equations are, solutions of above equations are given by the equations phi r is equals to 1 upon 4 pi epsilon naught volume integral rho d tau divided by modulus of r minus r days. Similarly, AR is equals to mu naught upon 4 pi volume integral JR d tau divided by modulus of r minus r naught. These are the solutions of above equations. And here d tau is infinitesimally small volume, and this is represented in this diagram that d tau is infinitesimally small volume, and its position vector is r dash, and here p is a point. There is a point P whose position vector is r, at which we have to find potential. At this point we have to find the potential, and its distance from the infinitesimally small volume, the distance of the point P from the infinitesimally small volume is modulus of r minus r dash. Now equation 6 is valid only when charges are at rest and currents are constant. Equation 6 is this. This equation is valid only when the charges are at rest and currents are constant. If rho changes with time, if charge distribution changes with time in volume d tau, then electric field associated with the charges will move with velocity c and time taken in traveling distance from d2 to p is given by modulus of r minus r dash divided by c. This is the distance, and the time is equals to displacement divided by velocity, and or we can say that time is equals to distance divided by speed. Now clearly, contribution to the potential at point P due to the charge in volume d2 at time t does not depend on the charge at time t, but it depends on the charge at time t minus modulus of r minus r dash divided by c. And in this case, the phi rt is equals to 1 upon 4 pi epsilon naught volume integral rho r dash t minus modulus of r minus r dash divided by c divided by modulus of r minus r dash d2. Similarly, a is equals to mu naught upon 4 pi volume integral j r dash t minus modulus of r minus r dash divided by c d2 divided by modulus of r minus r dash. And now we have to check that whether these equations 7 and 8 are the solution of inhomogeneous equations 3 and 4. We have to check that these equations 7 and 8 are the solutions of inhomogeneous equations 3 and 4. This is the equations 3 and 4. Now for that, put r dash, capital R dash is equals to modulus of r minus r dash, and in this case phi rt becomes phi is equals to 1 upon 4 pi epsilon naught volume integral rho r dash t minus r capital R dash divided by c d2 divided by r dash. And it is quite difficult to find the potential at point r dash is equals to 0. So we divide the volume in equation 9 in two parts. First part of the volume is a sphere of radius r naught about the point at which we have to find the potential phi, and second part of the volume is the remaining volume. Let phi is equals to phi 1 plus phi 2. Then apply del 2 on both the sides, then we get del 2 phi is equals to del 2 phi 1 plus del 2 phi 2, and we can neglect r dash divided by c is equals to small r minus small r dash divided by c in small sphere region. So we can neglect this term, so we can write del 2 phi 1 is equals to 1 upon 4 pi epsilon naught del 2 volume integral rho r t divided by capital R dash d2, and this will becomes equal to rho upon 4 pi epsilon naught volume integral del 2 1 by r dash d2, and finally we get del 2 phi 1 is equals to minus rho upon epsilon naught, and del 2 phi 2 is equals to 1 by r dash del 2 del r dash 2 r dash phi 2, and in this condition put the value of phi 2, then we get del 2 phi 2 is equals to 1 by r dash del 2 by del r dash 2 volume integral r dash into rho r dash t minus capital R dash divided by c upon 4 pi epsilon naught r dash d2, and we get del 2 phi 2 is equals to 1 upon 4 pi epsilon naught volume integral 1 by r dash del 2 by del r dash 2 rho r dash t minus capital R dash divided by c d2. For any function f is equal f t minus r dash divided by c. For any function f t minus r dash divided by c, we can write the del 2f by del r dash 2 is equals to 1 by c square del 2f by del t2. So we can replace the double differentiation. We can replace the double differentiation with respect to r dash. So we can replace the term del 2 by del r dash 2. So we can write del 2 phi 2 is equals to 1 upon 4 pi epsilon naught volume integral v 1 by r dash c square del 2 by del t2 rho r dash t minus r dash divided by c d2. And finally we get del 2 phi 2 is equals to 1 by c square del 2 by del t2 volume integral rho r dash t minus capital R dash divided by c divided by r dash into d2. And del 2 phi 2 is equals to 1 by c square del 2 phi by del t2. Now put values of del 2 phi 1 and del 2 phi 2 in equations. In equation del 2 phi is equals to del 2 phi 1 plus del 2 phi 2. So we get del 2 phi is equals to minus rho upon epsilon naught plus 1 by c square del 2 phi by del t2. And finally we get del 2 phi minus 1 by c square del 2 phi by del t2 is equals to minus rho upon epsilon naught. And it is clear from this equation that the equation 7 is the solution of equation 3. It is clear from that equation 7 is the solution of equation 3, and the potentials represented by equation 7 and 8 are called retarded potentials. Potentials represented by equations 7 and 8 are called retarded potentials.